Well, hello there, handsome fella. Have you ever been thrown down a staircase, or have you ever fallen over your own shoes? Because today we are going to talk about falling and throwing. And we actually derived a formula for falling and throwing in the last video about accelerations, which was the formula for constant accelerations, and that's what falling and throwing is all about. The formula we can see right here. Our spatial coordinate is given by 1/2 at squared plus v0 times t plus x0, and these two are just initial conditions, the v0 and the x0, and the a is our constant acceleration. While for the velocity, we actually have the velocity with respect to time is actually a times t plus v0. Now we're going to talk about two big cases, which are falling and throwing. What is falling and how does it differ from throwing? Well, the special thing about falling is that you are not throwing something. So the special thing about falling is that you have this constant accelerations and everything, but the special thing is that your v0 is actually 0. So you're not throwing something upwards, you're not throwing something downwards, you're not throwing something to the side, you're not throwing something to the left, because your initial condition of the velocity is actually 0, so you can just let it go. So let's let something go. Let's let falling go. So right here we have John, and John is like a bad boy, and he always has some coins with him, and he likes to throw things down. And this time he has found a well to throw things down into. And this well is 20 meters deep, and we're just going to assume that our acceleration is about 9.81 meters per second squared, which is the Earth's gravity acceleration, but we're going to just round it a bit to 10 meters per second squared. Now there are two ways to look at this problem. There's the red way and the yellow way. And I'm going to introduce Alfred and Bob right here, and Alfred is going to be the red guy and Bob is going to be the yellow guy. The first interesting thing is that no matter what inertial system we use, we are always going to have the same formula for our spatial function. Now we are going to talk more about Galileo transformations and inertial systems and formulas and such stuff, but first we got to get the basics, and this is the basics. So let's dive right into it. What do we have? Well, we have x of t is 1/2 at squared, the v0 is 0, and plus x0. So this is quite cool, but what does it actually tell us? Well, right now it doesn't tell you anything, because we have forgotten one last step, which is to substitute our actual acceleration for the acceleration placeholder we had in the formula. So right here we now got minus g, because this red guy sees the blue ball thingy here falling down with minus x coordinates. So the x coordinates is going to get lower and lower, so it has to be minus g times t squared. For the yellow guy, it's actually the other way around. Because he is right side up, he actually sees that the ball or coin is actually going away from him. So it's actually going up in his coordinate system, because his coordinate system is so tilted. So he is actually seeing a coin approaching the ceiling of the well, while the red guy is seeing a coin approaching the bottom of the well. Now the red guy has this formula, minus 1/2 gt squared plus x0, and the yellow guy has this formula, 1/2 gt squared. So are they different? Now let's look at it a bit further. Now we have a condition. The red guy wants that the coin actually gets to the bottom. The yellow guy wants that the coin actually gets to the ceiling of the well. So let's take that condition and put it into math. So if we want something to reach our position, it has 0 difference from our position, so it's actually 0 above us. So our x of t should be 0 when the thing hits the well bottom. And for the yellow guy, it's different. The yellow guy, it starts at 0. It starts at his position, and it should go x0 up to the ceiling. So he actually wants that his 1/2 gt squared reaches x0. Now let's calculate the times, and that's just a bit of math, and math, we all hate math, and we all can't do math, and math, oh no. But right here we have done a little bit math, and I've done it for you, and we see that t is equal to plus or minus the square root of 2x0 over g. And that's same for both people, and that's an important step. No matter from where you look, the time is going to be the same. Because the actual laws of physics remain the same. How you describe them can differ. It can be this formula or this formula, but the actual law behind it can't change. At least we're going to see that in the so-called Galileo transformations. We're going to talk about special relativity relatively late. Right now, let's focus on this t. This t is either positive or negative. Does that make sense? And no, it doesn't. This does not make sense. Because we say, oh yeah, after 5 seconds it's going to come down there, and 5 seconds ago it was already down there. Then you're going to say, no, John carried it with him. John came from here, and 5 seconds ago it was right here, and he just came there and you threw it down, and in 5 seconds it's going to be down here. So what the actual fuck? What is it? Like, this is nonsense. And it actually is nonsense, because we don't have gotten the right thing. We didn't include a very important detail. We didn't include that before t0 this guy still had the coin in his hand, so the coin could not move at all. If we added that condition, everything would be fine and we would only get the positive t. Now with our failed, in quotes, condition, we actually get 2 times. But don't worry, we can just cross out the wrong time. You can just say, oh, that's wrong, because it's actually below 0 seconds, and that doesn't make sense for our calculations. Interestingly, if you just put 20 meters right here and 10 meters per second squared right here, you actually get the unit of seconds. And that's very interesting. Once again, you always should get the right units. No matter where, you can always rely that the physics behind it is going to give you the right units, and that's so important. You can't even believe it. Because by actually just looking at the units, you can guess if your thing is right or wrong. And if you have done a mistake, just look at the units and you're going to find your mistake. There's nothing better than looking at units, I can tell you. I have done physics for quite some time, and units are just the best thing there is. And apparently I can't pronounce a thing. So let's talk about the velocities. And this should hopefully not scare you, because actually it's quite easy what we did here. We actually just added the v is equal to g times t, or in this case minus g times t, and in the yellow case it's still the positive g times t. And we could actually substitute the 2 seconds right here and right into this, and this is 10 meters per second squared, and we get minus 20 meters per second for red and 20 meters per second for yellow. But wait a second, didn't I just say the results are always going to be the same? No, I didn't say that. I said that the underlying formula is always going to be this. If the underlying formula is going to be the same, they're going to describe the same process. They're going to get something like the same times. And for yellow, if this thing is moving down for us, it's actually moving up for him. So it's perfectly reasonable that he sees us at plus 20 meters per second, while everyone else is probably going to see it at minus 20 meters per second, except you're making a handstand right now. So these 2 different results are actually not wrong. Each result is correct, even though they're different, just because we have different systems in which you look at this. So by now you can probably guess that choosing your system is quite important. It can, for one, make your formulas more easy. This formula is easier than this one. But it can also lead you to thinking you have done a mistake, even though you didn't. or thinking you've done it right even though you did a mistake. So in each calculation you should always remember what actual system you are looking at. Where are you looking at the problem from? Because that's sometimes quite important. And this substitution I did right here, that's just math and physics and blah, and we're going to put the G into the G and we're going to have some fun with it. So let's look what I actually did right here. So I actually had this minus G times this strange square root, and I saw here's a G and here's a G, and this one G is under the denominator and the other thing is above it. So what are we going to do? Well, we're going to try to shorten them, to cut them out. Because G over the denominator and G under it both cancel out. So let's look at it. How do we do it? Well, we actually have to convert this into a square root first. So we actually take the square root of G squared, which is just this G, and then we can use the laws of the square roots and put them two together. And then we have G squared times 2x0 over G squared, and then they cancel out and we can cancel this with this. And we only get the remaining G, the remaining 2 and the remaining x0. So we actually have left 2x0 times G, and all of that under a square root. So let's calculate it. And if we substitute 20 meters right here and we substitute 10 meters per second squared right here, we actually get the minus 20 meters per second in the right units once again. And once again I want to remind you that we started with the time, and from the time we could derive other units. So if we are going to talk about velocities, about movement, we almost always want to get the time first before solving for other things. You almost always want to get the time first before solving for the space or the distance if you want, or the velocity. Now there's something else which I wanted to talk about, which is throwing in one dimension. And in this case, we are not going to start with an initial velocity of 0, which is just plain boring, but we're actually going to have this guy here. Or maybe it's a girl, maybe it's Mary. Mary has gone here with a tourist guide, and she doesn't really like the tourist guide, so she kind of spaced off a bit, and now she's standing next to a cliff. And Mary likes to throw things too, so she's a friend of John probably. And today she got that one giant stone, and she's just going to throw it right up into the air. And it's going to move only like 1/2 of a centimeter, or maybe even less. And we're going to approximate that by a one-dimensional throw. Because two-dimensional throws are a bit more difficult. Not really, but a teeny tiny bit more difficult. So we're going to do it in the next video of the two-dimensional throws. Right now we have a throw that goes 1 meter per second up, and it actually has to fall 4 meters deeper than it started from. So how do we do that? Well, we just take the same old formula. We take the same old formula for it once again, which is x of t is minus 1/2 gt squared plus v0 times t plus x0, and once again I substituted minus g for the a. Right now we also have a condition once again. What is our condition? Well, our condition is that we are going to reach 4 meters deep, or 4 meters deeper. So from this point here, it's 4 meters downwards, so minus 4 meters. So we actually trying to reach minus 4 meters, and our x0 at that point is 0. If we would look at it from this position right here, our x0 would actually be lower. If we would look at this from this position, our x to reach would be 0, and our x0 would be probably 4 meters. So it's always changing depending on where you look from. But the result is going to be the same, which is cool. So minus x, which is our position to reach, minus 4 meters, is equal to minus 1/2 gt squared plus v0 times t. And we can solve that a little bit. We just multiply with 2, and then we divide by g, and then we multiply with minus 1, or we divide by minus 1, however we like it. And we get this right here, and this we can solve with the PQ formula. Now here we have p halves squared plus or minus the square root of p half. Oh, sorry, this is p half plus or minus, also minus p half plus or minus the square root of p half squared plus q. In this case, it's actually minus q. In this case, the q is minus 2x, so we have plus q. It doesn't really matter. It's just math in the end. And I'm not going to try to teach you math. I'm going to try to teach you physics, which is quite important. And of course, in the end, you're going to need math, but you have to understand what math does before you can understand what physics does. So right here, we actually have just calculated some time, and what the time is actually interesting, because this time is actually 1/10 of a second plus or minus the square root of 9/10 of plus or minus 9/10 of a second. There shouldn't be a square root right there. This is better already. So we actually have minus 0.8 seconds or 1 whole second. So now once again we can just cancel out the minus 0.8 seconds, because for us that's total bullshit, because we're never going to assume that something started before we actually started to measure it. So for us that here, right, once again is bullshit, because the physics and the math right here are correct, because actually if you continue this here, before 0.8 seconds, if it had traveled all the way only this path right here, it would have actually started in the ground. But because before 0 seconds we actually had another spatial coordinate function, we actually just have to assume that our t is bigger than 0. So that's why we can just assume it back here. Now we can substitute it for the velocity once again, and we have the initial velocity right now, so don't forget that, and it's minus 10 meters per second squared times 1 second plus 1 meter per second, which is minus 9 meters per second. So it's actually falling down here with minus 9 meters per second, which is actually quite fast. That's actually about 20 miles per hour, so quite interesting. And once again, of course, I as a physician did it once again with the formula from up here, and I substituted a bit, and I multiplied with g and did a little bit of shortening and cutting and things and stuff. And once again, I also get a plus or minus something, and if I substitute the values here, right here, I actually also get minus 9 meters per second. But of course, once again, I have to cancel out the wrong results, which would be this plus right here. This plus is wrong. So actually, if I substitute everything correctly, I actually get the minus 9 meters per second. There was something else I wanted to talk about though. This right here is quite interesting, because this right here shows you another basic principle of physics, which is that if you generalize a formula, it has to apply for the specific case as well. We generalized our falling by adding the v0. We just added that. That's an addition. We generalized the whole thing. We didn't assume anymore that our v0 was going to be 0. We generalized it. So of course our generalization and all of our formulas for our generalization also have to apply for the non-generalized thing. So if we put v0 equals 0 here once again, and then this is 0, this is 0, and we get actually the same formula as before, the square root of 2xg over g squared, or 2x over g. So let's go up again, and we actually have it here, 2x0 over g, and that's the square root, and we actually had plus or minus as well, and we actually had to as well shorten the minus. So once again, if we do that for the velocities, and we cancel out this velocity squared, we actually get the square root of 2g times x0 once again, and that's once again the formula we had right above there. So this basic physical principle is quite interesting. If you generalize something, it has to also apply for the special case. And that's something you always get reminded of, especially if you're talking about the theory of general relativity. Oops, that was quite mispronounced. The theory of general relativity. Because it seems quite strange. Things are getting shorter, time is getting shorter, and mass is getting bigger, and energy is kind of strange, and everything is weird. But if you actually talk about velocities that are below 1/10 of the speed of light, which is every velocity we know right now, then we actually get our normal formulas. So generalizing must apply for the specific case as well, and you're going to get reminded of that in physics quite often. Now this was the video already. I just wanted to talk about these two special cases because in the next video we're actually going to talk about the multi-dimensional throwing. So we're not only going to throw in our 1D space, but actually in 2 dimensions or 3 dimensions in the very end. And we're going to talk about vectors right there and the principle of superposition, or superposition principle, which is quite interesting because it tells us how to deal with more than 1 dimension. Still, I hope you weren't annoyed by my German accent, and I hope you can leave a like or maybe a comment, and I hope we are going to see each other the very next video. See you then.